Hi, hello, how are you? Craig Chapman here with your second part in experimenting with neural network simulation. I'd like to start with a brief apology if there is a difference in audio quality than this part. I'm actually recording from a different location to usual with a different microphone, and I'm hoping it'll all work out okay, but just in case there are issues, apologies in advance for that. Also, this is part 2 of my video series. In part 1, we looked at how a neural network is constructed. Unfortunately, in the first part, I did have some mathematical blunders in the examples that I gave. The content of the video was fine, but some of the numbers were off. So I've gone back and annotated corrections in the original video. If you need to see them, feel free to go back and re-watch, but I believe the content still stands as fine the way that it was. So we're going to go ahead and get started building a neural network simulation in this video. And what we'll be doing today is simply building the neural network. We may get to processing input through that network, but what we're not going to look at just yet is training the network. That's going to come in a later part. So we'll get started just building the data structures that we need for our neural network simulation. I would like to dive straight into the IDE and get started, but before we do, I think it would only be fair to open up Excel and look at how we'll construct some of the data types in memory. So I'm going to switch over to Excel first, and then we'll get started in the IDE building our neural network code. Okay, so for most of you familiar with object-oriented programming, it might make sense to begin by writing a class which represents a neuron, and then that class would have properties with, for example, the weights or the inputs and so on. And this would make sense if what you were really aiming for is an easy to work with API, if you wanted to be able to add and remove neurons at will, and so on. That makes a lot of sense. But unfortunately, in terms of processing, it doesn't make sense. The reason is, for example, if you want to fetch the axon value from a neuron in a previous layer, then what you'd end up actually doing is calling a getter on the previous neuron. And that's a function call that's going to cost us some CPU cycles. You'll have getters and setters and things like that going on. And on top of that, the amount of memory that you would consume with the classes is going to have some overhead. It's going to be larger than if we store the neuron values just as a flat array in memory, which is what I plan to do. But there is another reason why we want to do it this way. You'll remember in the previous video I talked about how CPUs have limited cores, limited number of threads, and as a consequence there's a limited number of neurons you can simulate at any one time on a CPU. Well, there is a piece of hardware in most computers which is much more suited to parallel processing, and that's the GPU. So if you use the graphics processing unit, it's very good at doing floating point math in massively parallel situations. At some point in the future, maybe for this video series, maybe not, I'm considering upgrading the implementation of my neural network to run on the GPU instead of the CPU. And so it makes sense to have data structures that are easy to send to the GPU. And flat arrays are about as easy as it gets. So what we're going to do is work with flat arrays of data. And this is why I brought us into Excel for a moment, just to look at an example of what that might look like. If you remember back to the previous video, we had a neural network constructed of 4 input neurons, 3 hidden layer neurons, and 1 output neuron. So we actually have 8 neurons effectively. So let's suppose we reserve N0 through N7. And this is 8 locations in memory where we'll have the axon values for our neurons. So I'm just going to put a random value in, 1, 2, 4. And I'm going to make that the same for all of my neurons. So this flat array of 8 items here, that is my neuron axon values. So what I can do is I realize that the first 4 of these are in layer 1. So that's my first layer. The first 4, so 0 through 3 in my first layer. In my second layer, I've got another 3 of them, and in my final layer, I have 1 more axon value. So what we can do is now set up the synaptic weights, or rather the synapses. So if we consider this to be our neuron array, this would be our weights, or synapses actually. The synapses array is going to be an array with 2 parts in each element. The first part is going to be an index into the neuron axons array, and the second part is going to be the weight value. So our weight value 0.345 or whatever it might be, I'm going to put that in for all of these neurons. And then the index value, well, the first of these, we're going to say that we're on, let's start with, I guess I should skip layer 1. Yes, so layer 1 I'm going to skip for the moment, so I'll leave space for 4 weights in layer 1 because each of the input neurons has a single synapse attached to it. So we're now looking at layer 2. So in layer 2 we have, let's see, neuron number 4, which is this one right here, and neuron 5 and neuron 6, those 3 neurons. And so we have, let's make space for them. So this is going to be these 3 right here. I'm going to make them a slightly different color. Let's make them blue. That's going to be our first neuron's synaptic weights. Our second neuron in this layer, actually I need 4 of these. In the second neuron in layer 2 is going to have 4 input values, and I'll just change the color of that to let's say yellow, and then we'll have another 4 which I'll just change the color to, let's say, gray. Okay, so I'll just extend these weights all the way down. Now what we'll have for the index is, well, the first neuron in layer 2 is N4, and it's going to be connected to neurons 0, 1, 2, and 3. So what we'll do is we'll put in the indices 0, 1, 2, and 3. The second neuron in layer 2 is going to be neuron number 5. It's also connected to 0, 1, 2, and 3, as is the third, which is neuron 6, connected to 0, 1, 2, and 3. So what we can do when we pass in our neural network into whatever function is going to be processing it is we can say, you know, layer 2 consists of these neurons. So the layers, if I create one final array here, let's say layer 1, layer 2. Well, layer 2 is going to have the value of, if we're starting here at 0, 1, 2, 3, we start at position 4 in the synapse array. So it's going to start at 4, and it's got 12 items in it. So it's going to go to 16. Actually, that was layer 2. Let's get that right. So layer 1 is going to be 0 through 3. That's going to be layer 1 synapses, and then layer 3 synapses. Well, bearing in mind layer 3 is a single neuron, but that single neuron is connected to N6, N5, and N4. So that would be 3 more values on the end of here. So that's going to be 17, 18, and 19. So effectively what we can do now is we can pass our array of neuron axon values, so our array of neurons, our array of synapses, and our array of layers as 3 different pieces of data into our neural network processor. And it can then run through and say, well, I'm looking at layer 1 now, so I need to look at synaptic weights 0 through 3, sum them up, do the processing on them, and so on. And then we can move on to layer 2 and onto layer 3. But what do we do about the input layer here? So if you look at layer 1, we have no indices here, and our layer 1 neurons are 0 through 3. So what do we do to get the input values for these neurons? What I'm going to do is I'm going to extend the neurons layer for a moment, and we'll put in some input values. So let's say we're going to put in I0, I1, I2, and I3. Well, these will be our input values. Let's put a different random number in here, 254, for example. And so when we look at our indices, we're indexing from 0 right here. So we're actually looking at index number 8 for the first input, 9, 10, and 11. So what we can do is pass in our neuron array with our inputs at the end of that array. And then when we want to process different inputs, we simply find these values and replace them with our next set of input values. Okay, so let's go ahead and begin modeling this in code. Okay, so here I am in the IDE and I've created an empty package, pkg.ai, and I'm going to go ahead and add a new unit to this package, and this unit is going to be my neural network interface. So I'm going to call it ai.neuralnet, and actually I'm going to lowercase all of these, neural net, and in here I'm going to put an interface, type I neural net equals interface, and we're going to have some methods in here. Now I'm not actually going to put the methods in right now, but I'll put some examples in. So for example, we're going to have methods such as query network to query the network for some results, and we'll have a method for train to train the network, and so on. So that's what we're going to put in the interface section, but for right now we don't need any of those. What we're going to do here is save this off as an interface for our package in the interfaces section, and I'm just going to name it AI neural net.pas, and then we're going to start working on an implementation for this interface. So I'm going to add a new unit to my package, and I'm going to put in there ai.neuralnet.custom. Now the reason I'm doing custom is I'm going to have a base class which contains the functionality of initializing and configuring the neural net, and we'll be able to derive from that base class to create our actual neural net class. So what I'll do is I'll put in a type t custom neural net. Custom neural net is equal to a class. It's a t interfaced object, but I'm not actually implementing the neural net interface yet. This is just the base class functionality. So I'll go ahead and save that off, and that's going to go in source implementation ai.neuralnet.custom.pas, and then I'm going to create a third unit, add new unit, and this is going to be our ai.neuralnet. And so in the last video we talked about the perceptron neuron. Well, a bit of a confusing terminology, but there is a type of neural network called a perceptron, which is the type that we're building here. So we're actually going to build a perceptron network, even though the activation function for each of the neurons may be the sigmoid function rather than the perceptron. So it's the type of network that we're building. And this particular implementation is going to run on the CPU, so I'm going to put CPU in there, and then we'll save that off as AI implementation. So this is going to be ai.neuralnet.perceptron.cpu.pas. Bit of a long file name there, but it just helps to keep things separated out. So we're going to use this in here, the ai.neuralnet interface and ai.neuralnet.custom, which is going to be our base functionality, and then we'll have let's call it t-perceptron. So t-perceptron is the type of neural network that we're building, not the activation function. It is a class of t-custom neural net, and it does implement the I neural net interface. Okay, so this is effectively the class that we're going to be building, but it's deriving from t-custom neural net because there's a lot of functionality we're going to put in the custom class, which is base functionality. So that's what we're going to start with. Okay, so I'm going to begin by putting in a private section here for storing some of our data, and a public section for our constructor. And I'm going to put some parameters in that constructor in a moment, so this is going to be a reintroduce because they're parameters that don't exist on the t-interfaced object base class. And then we'll also have a destructor destroy override. So what do we need in terms of data in our t-custom neural net? Well, one of the first things we're going to need is the three arrays. Or the first thing we're going to need to add are the three arrays. And the arrays were arrays of neurons, synapses, and layers. So let's do the neurons first because that's the easiest one. We'll have F neurons, and in fact I'm going to call this axons. F axons, is an array of t axon value. So we need to define the type t axon value. We're also going to have f layers, which is going to be an array of t layer, and we also want the f synapses, which is going to be an array of t synapse. So let's define some of these types. Well, t axon value is just a single, so we're going to use single point precision floating point math, and actually I'm going to put a new type deck in here. The t synapse is actually a record, and the record points to a previous axon. So we'll have axon index, and that's going to be an index of the axon of a previous neuron in the axons array, and that's going to have a tnet index data type. Tnet index is just a uint32. So I've put these two values in here as the basic data types that we can alter at some point in the future. So if I wanted to go to double as the floating point type, for example, or if I wanted to change the indexing of the arrays, then I would change that. So those are the two types that are the base, and then we have our synapse, which has an axon index, but our synapse also has a synaptic weight. So weight is t synaptic weight, and a t synaptic weight is the same data type as a t axon value. So all I'm doing there is making sure that our synaptic weights are also single point floating, single precision floating point values. Okay, so that's our synapse, and we now need our layer. So t layer is going to be a record, and this record is going to be, let's see, first synapse, which is a tnet index. Last synapse is a tnet index. So effectively, when we want to send this data, if we were writing the GPU version of the class, for example, and we wanted to send our network up to the GPU to be processed, we would send in these three arrays. So this is the neural net data, but we're going to want to store some properties of the neural net outside of its actual data. For example, we might want to have f total neurons, and that's going to be a tnet index value. We might want to have f input neurons, tnet index to tell us how many input neurons there are, f output neurons, tnet index to tell us how many output neurons there are. So all of those values are useful pieces of data which we don't actually need for the implementation, but we might need for initializing the network or passing data into it and out of it and so on. So we're going to put those values in, and I'm sure there will be more values that we need. In fact, let's just go ahead and add f layer count as a tnet index as well. So that tells us how many layers we have in our neural network. Now, in order to initialize this neural network, we're going to come to this constructor, and we're going to pass in neurons per layer as an array of tnet index. So what does that mean? Well, if we have 3 layers, then we'll have 3 items in this array, and those 3 items will be, as in our example, 4, 3, and 1, for 4 neurons in the first layer, 3 in the second, and 1 in the third. So this array actually tells us both how many layers there are and how many neurons there are in each layer. Let's go ahead and flesh this class out. Inherited create, inherited destroy. Now, before we write the constructor and start calculating how much space we need in memory for everything, let's take a look at actually the destructor, because it's the easier one to do. So we're going to go ahead and take the 3 pieces of information that we have here that are arrays. Now these are dynamic arrays. They're going to be allocated when we create the class, so we need to deallocate them when we dispose of the class. So we'll have set length of f axons to 0, set length of f synapses to 0, and set length of f layers to 0. So that's just going to dispose of the memory that we allocate for our neural net. Now we need to figure out how much memory do we need for this neural net. Well, the first thing we need to do is figure out how many layers there are. We need the layer count, and that's the length of this neurons per layer array. So f layer count is length of neurons per layer. Now there is a possibility for an error occurring here. If f layer count is 0, again, I'm going to raise an exception for this, and I'm going to be lazy and just raise an exception class. And let's put neural network requires at least one layer. So that's just saying you didn't put enough layers in the constructor. So that's get layer count. Okay, so now we need to figure out how much data to put in each of these arrays. Well, the first one, the easiest one, is the layers array. So what we're going to do is set length f layers to layer count, and that's going to be f layer count. Okay, so that's the easy one done. Now we need to figure out how much data we want in the, let's say, the axons array. Well, to do that, we need to figure out how many neurons there are total in our neural network. So I'm going to say f total neurons get some neurons per layer, NE neurons per layer, and then we're going to create a function tcustom neural net dot sum get some neurons, and we'll pass in neurons per layer array of tnet index, and that's going to return a tnet index. Okay, so we'll Control-Shift-C to put that method into our private section, and actually I'm going to go ahead and create another private section to keep the methods separated from the members there. Okay, so to sort this one out, what we need is var idx tnet index and an L tnet index. So we're going to say L is equal to length of neurons per layer, and so that's going to give us the number of layers that we're going to have to cycle through. If L is equal to 0, then begin exit. So we're going to set our initial result to 0, and if we pass in an array with no layers, then we'll just bomb out returning 0 as a result. Then we'll do a for idx from 0 to pred L, which is our layer count, begin, and just in case you're wondering why I took the length of the array here a second time rather than just using layer count, the reason is just in case this method ever gets called from anything other than our constructor. It shouldn't, and I can't see any reason why it would, but it's just call it best practice if you like. So I'm going to include sysutils because I noticed that exception wasn't included, and return to this method. So we're in our loop, and we're just going to do result equals result plus neurons per layer idx. So that's going to sum up the total number of neurons in our neural network based on the neurons per layer array. And so then down here we can say total neurons is get some neurons and pass those in. So that gives us our total neurons, but that isn't the size of our axon array. Remember that our axons from the example contained all of the axons for the neurons and the input data. So we also need to figure out how much input data there is, and that's the next parameter, f input neurons right here. So let's go ahead and figure that out. F input neurons is actually the neurons per layer for the input layer, which is always going to be layer 0. So that'll give us our input neurons. And while we're here, let's set the f output neurons as well. Neurons per layer, and this is going to be the pred of f layer count to get the last layer in our network. So now we have sufficient information to decide how many axon values we need. Set length f axon, was it f axons did I put? okay, f axons, and it's going to be the f total neurons plus f input neurons. So for each input neuron, we're going to add an additional axon value for its input value. Okay, and the final array that we need to initialize the size on is the layers array, the synapses array. Now this is going to need another function. So we're going to say, did I have a parameter for total synapses? I did not. So let's put f total synapses tnet index, and we'll say f total synapses is going to be equal to get some synapses neurons per layer, and then we're going to go ahead and take a copy of this get neurons function, get some neurons, and modify this out to be our get some synapses function. So Control-Shift-C to include that in the class header there. Okay, and then what we do is this. First we set the result, so we're doing our test for the length of the array up here, just as we were before, but now we're setting the result to be the number of neurons in the input layer. So neurons per layer in layer 0. So that's going to get one synapse per input neuron, which we know that the input layer has one synapse per neuron, or one synaptic dendrite, if you like, per neuron. Okay. Then we're going to say if L equals 1, then begin exit. So what we're saying here is it is entirely possible that we ask for a neural network with a single layer, the input layer only. Now, I don't think that type of neural network would be particularly useful, although it might be useful for testing a single neuron and how it behaves. So it's not like we're likely to ever use one that size, but if we do, then we can exit here because we only have one layer. We don't need to count the remaining layers. And then for the remaining layers, we're going to loop from layer 1 to pred L. And what we're going to say is result is equal to result plus. Now we want the number of neurons per layer in the current layer that we're examining, and it's connected to every neuron in the previous layer. So we're going to say neurons per layer pred IDX. We're just going to multiply those together, and that's going to give us the sum of the synapses to connect each neuron in the current layer to each neuron in the previous layer. We add that to the result, and that will give us our total size of the synapses array. So we've done f total synapses. We now need set length f synapses f total synapses. So that's our array scaled out and built, and we now need to look at initializing it. Okay, so now we have our memory allocated. We need to start initializing this array. And the first thing we're going to initialize, I guess, would be the layers. So let's make a function or a procedure, initialize layers. And I'm going to pass in neurons per layer. And then we'll go flesh this function out. So up here we'll have procedure t custom neural net dot. And this is going to be initialize layers, and it's going to have neurons per layer array of tnet index. Begin and end, Control-Shift-C to put that up into our class. Right, so to initialize the layers, the first thing we need to do is, let's see, we're going to need an index, so we'll have tnet index. And we already have the layer count at this point, but let's go ahead and have LTNet index for the layer count as well. And we'll get the layer count manually one more time. So we'll say L is equal to length of neurons per layer. If L is equal to 0, then begin exit. And then we'll start initializing our layers array. Now, the layers array contains the first and last synapse for each of the neurons. That's what we're looking for. Now in the first layer, that's very, very easy. F layers, the first layer, first synapse is going to be 0 because that is the first synapse, it's the first neuron. F layers 0 dot last synapse is going to be the number of neurons in this layer. So it's neurons per layer for layer 0. Okay, that's what we need for the first synapse. So this is input layer. Okay, so now let's start working on the subsequent layers. So we're going to set up a for loop for idx is equal to layer 1 to pred of L. Okay, and what we're going to do for each of these layers is F layers, and it's going to be idx for the layer number, dot first synapse. Well, the first synapse in layer 1 is going to be after the last synapse in the previous layer. So what we'll do is just F layers pred of idx dot last synapse. So that's going to give us the last synapse in the previous layer. And actually what we want here is going to be the successor of the last synapse in the previous layer. So that's going to be suck. Now we need to calculate how many synapses there are in the current layer. Well, we've done that once before, so let's do the same again. So we're going to set up layers idx dot last synapse, and this is going to be F layers idx dot first synapse plus the number of synapses in this layer. The number of synapses in this layer is neurons per layer for the current layer, which is idx, multiplied by neurons per layer in the previous, so pred idx layer. Okay, and so that's going to give us the last synapse in this layer. And then we'll cycle the loop again and it'll repeat. Now we do need to put our little check in here. If L is equal to 1, then begin exit, because we don't want to process layers above 1 if there's only one layer in our network. Okay, so that should initialize our layers. And actually, before we proceed, maybe I should dump these values and test that they're working. We'll do that at the end. We'll dump all the values out and debug afterwards. So the next thing we want to do is to initialize the synapses. So I'm going to put another function in here, and this is going to be procedure tcustom neural net dot initialize synapses, and this one is also going to accept the neurons per layer array of tnet index. Okay, and let's go ahead and add that into our class, and then in our constructor we'll call that function as well, initialize synapses neurons per layer. Now to initialize the synapses have a synaptic weight, which we're just going to set to a random value for the moment. There are better ways of initializing the synaptic weights, but for the purposes of this tutorial series we'll just randomize them. And we also need the index pointing into the axon array for the axon that we're getting our value from. So this one gets a little more complicated, but not too bad. Let's start the way we started all of these functions by getting the length. So we'll do a tnet index, and we'll say L is length of neurons per layer. If L is equal to 0, then begin exit. So that's just going to dump us out. Right. Okay, so the first thing we're going to do is sort out the synapses for the input layer. The input layer is relatively trivial. So what we do for the input layer is, for idx is equal to, let's say s idx, synapse index, is equal to, and then we need f layers, the input layer is layer 0, dot first synapse, so we're going to cycle through from the first synapse to f layers input layer dot last synapse do begin. Now each of the synapses in the input layer is pointing to an input axon, and we know where the input axons begin. They begin at total neurons plus 1, or suck of total neurons. Actually at total neurons, because we're indexing from 0. So what we'll do is we'll say f synapses sidx dot axon index is equal to, and then because we're in the first layer, the first synapse is actually going to be 0, and the last synapse is going to be the end of the input neurons. So what we'll do is simply set sidx, and then add that to f total neurons plus sidx. Yeah. So this is going to be input layer right here. Now we need to start working on the subsequent layers. So what I'm going to do first is make sure that we have subsequent layers. We're going to say if L is equal to 1, then begin exit and bomb out of there. And then we're going to set up a layer index. So I'll set L idx is going to be equal to 1. And that's going to be our first layer after the input layer. So L idx is tnet index. Now what we actually need to do for each of these layers is we need to find the axons in the previous layer. So let's see, we can find out axons in previous layer. That's going to be neurons per layer of item L idx, so that's our layer. And actually it's going to be pred of L idx. So that's going to tell us how many axons there are in the previous layer. We also need the first axon in the previous layer. If I set first axon in previous layer, and we need to give its index, well, we're coming in from having done layer 0, so the first axon in the previous layer is axon 0. That's the first in the input layer. So we're going to set that outside of our while loop, and then build a while loop, while L idx is less than L, because that's our layer count to begin. So then for each layer, for each of the layers that we cycle through, we'll get the number of axons in the previous layer, and we have the first axon in the previous layer for the first iteration. So having this information, we now need to cycle through each of the synapses in this layer, and effectively we're going to cycle through the number of axons in the previous layer. So we're going to say for synapse idx is going to be f layer, the current layer, L idx, dot first synapse to f layer L idx dot last synapse to begin. So we're cycling the synapses now. F synapse sidx is going to have its axon index set to, and it's going to be, I think we need to do an axon increment. Yeah, so let's set this axons in previous layer out. We'll leave that there, and we'll have an AIDX, axon index. The axon index is going to be set to the first axon in previous layer, and so we'll set that to AIDX. Then we're going to increment the AIDX, so that's going to increment us to the next axon for the next synapse. If the axon IDX becomes larger than the sum of first axon in previous layer plus axons in previous layer, then begin. AIDX is going to be set back to the first axon in previous layer. Okay, and so as we loop through the synapses, we're incrementing the axons and then looping back to the first axon in the previous layer. Now, once we've done all of that for each of these synapses, we're then going to increment onto the next layer. And before we increment to the next layer, we need to fix our axon indices. Let me go ahead and put some of these variable names in. So we've got first axon in previous layer. Oops, that didn't work. First axon in previous layer, tnet index. Axons in previous layer, tnet index. Our AIDX, SIDX, and LIDX are already in. So this is going to be set synapses in layer. So that's going to set the synapses in this current layer. Then we need to update the two variables, the first axon in the previous layer and the axons in the previous layer. So the first axon in previous layer is now going to become first axon in previous layer plus axons in previous layer. The axons in previous layer, well, we're actually going to come back around and get the axons in the previous layer on our next iteration of the loop, so we don't need to set that. We do need to increment LIDX so that we're on our next layer. So let's say update for next layer. Okay, F synapses, F layers, first synapse, F layers. And why does it not recognize F synapses? There we go. Okay. Alright, so I think that loop should get us set up with all of the synapses correctly set. And I'm going to have to test this, of course. So what I'm going to do now is build a test function. And the test function is simply going to dump out the values. Actually, there's a couple of things that I've forgotten and we need to go back and do. So the first thing is in our synapses, everywhere we set an axon index, F synapses, SIDX dot weight, we're going to set to 1 divide random of 1000, just to give it a random weight. And I'm going to do the same down here. Where are we? Synapses. Weight equals. Okay, so we're setting some random weights in there. And the next thing I need to do, we're going to do one more initialization. So I'm going to initialize the axon array. And this is going to be procedure t custom neural net dot initialize axons. And I don't need to pass in, interestingly enough, I don't think I need to pass in my neurons per layer this time. So what we're going to do is for IDX is equal to 0 to pred the length of the F axons array, because this is going to give us all of the axons, including the input axons. And we're going to set F axons, IDX, and I'm going to initialize all of them to 0. However, if IDX is greater than F total axons, or neurons rather, then begin. And we're going to set F axons IDX to, say, 200. Now the reason for this, and this is actually kind of a temporary thing, I'm going to come back and make sure that everything is set to 0. But the reason I'm putting 200 in here is when I initialize this array, I should be able to see specifically which are the input axon values and which are just the regular axons, which are set to 0. So I'm now going to write a function which will dump out all of the data that we've written into our array, and then I can compare that data with our predicted model. So I'm going to pause it here, I'm going to go and write the dump function, and then I'll come back and we'll see how we got on. Okay, so I added a function called dumpNet to our custom neural network code. So if I come, or dump arrays rather, so if I come take a look, I'm just getting a string list, and I'm adding all of the axons to the string list. I'm adding all of the layers, and then I'm adding all of the synapses, and then I'm simply saving that out to a file. And I created a test program, dumpNet, which, if we go take a look at the source code, this is just a command line application. It's just creating a custom neural net with 4 input, 3 hidden layer, and 1 output neurons, and it's dumping the values after initialization to our test.txt. And we do have a few problems. The first problem is this application crashed. And the reason it crashed is because when I initialize these synapses, if we take a look at where I'm using random, random can return a 0. So 1 divides 0 gives us a divide by 0 error. So I've added suck of random 1000 in both of these locations just to make sure that we get a non-zero random value. Then I run it again, and the output looks like this. And the first thing I notice is my axons have only 3 input values here, and we have a 0 in element 8, which is incorrect. So I'm going to come back in, and that was actually a very simple problem. In initializing the axons, I used greater than total neurons. I should be using greater than or equal to total neurons. So if I run my DumpNet application again and go take a look at the refreshed output, so I now have the correct 200 values coming out in my input axon zone, and the axons are numbered 0 through 7. That's all working out just fine. Now, my first layer is synapses 0 through 4. That's actually correct. So 0 through 4, these are my input layer axons, and the axons point at 8, 9, 10, oh, actually it's 0 through 3. So actually that is incorrect. So I'm getting synapses 0 through 3 are the ones that I should be looking at. And I'm getting axons 8, 9, 10, and 11 for those 4, which are 8, 9, 10, and 11. So we're actually getting the correct input axons in our first synapse. The rest of the synapses go horribly wrong, and we're going to look at that. But first, let's look at this layer issue. So we're looking at the first and last synapses, and I'm getting 0 through 4 should be 0 through 3. So let's go and see if we can correct that. So when I initialize the layers, I'm saying that the first synapse is 0 and the last is neurons per layer. Well, that should be the pred of neurons per layer. So that will correct that one issue there. If we go ahead and run a build and we go take a look at the refresh, I guess I need to do a clean build. So we'll do a clean all and build, and then we'll run the application again and take a look at the output values. And yes, I want to reload. So we're getting the first layer is now 0 to 3. So synapse is 0 to 3, and ignoring the weights for the moment, the values are 8, 9, 10, and 11, which are the correct axons. So our first layer of synapses is working. The next set we get is 4 to 16. So let's take 4 to 16 out of the running here. And 4 to 16, the axons should be pointing at, well, the first axon is 0 here. Well, that's correct. 1, 2, 3, and we have how many axons do we have in the hidden layer? So we're actually looking at the hidden layer now. We have 3 axons in the hidden layer, and each one has 4 axons that it's pointing to, 4 synapses. So that's 1, 2, 3, and 4 for the first hidden layer neuron. So that is working. The second hidden layer neuron should be starting back at 0, 1, 2, 3. But what we're getting is 4, 0, 1, 2. So obviously I've got another greater than issue going on here. Then we should get another 4, and let's see if I've got that right. So the layer is off for this one as well. We'll come back to that. But let's see if we can correct these axon values. They should be going 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3 for the hidden layer neurons. So let's go take a look at our code. And where we're initializing the synapses, we're saying loop through the first synapse to the last synapse, and we are incrementing the axon index, and we're saying if greater than, should be greater than or equal to. So let's go ahead and do a clean build, clean all, and build all, and we'll run this again, and we'll refresh our output here. So again, we've got 8, 9, 10, 11, that's correct, we know that. So the first hidden layer is 0, 1, 2, 3, the second layer is now 0, 1, 2, 3, the third hidden layer neuron is 0, 1, 2, 3, So these synapses are correctly indexed. And then in the final layer, I'm not sure, let's see, axon 0 is incorrect. In fact, in the final layer we should have, yes, 3 synapses. The first one should be pointing back at one of the input layer axons. So let's see what's going on here. Our first axon, 1, 2, 3, 4, they're our input layer. Now 5, 6 and 7 should be pointing back at, let's see, that's incorrect, 0, 1, 2, 3. 4, 5, 6 and 7 should be pointing back at 0, 1, 2, 3. And then the output neuron, have I got too many axons? No. There's our 4 inputs, 3 hidden layer, and our output neuron. So our output neuron is 7. So 4, 5 and 6 are the values we should be seeing here, 4, 5 and 6. And what we're actually seeing in the last layer is 0, 4, 5. So something's going wrong in our last layer as well. Let's go and see if we can figure out what that is. So when we get to neurons per layer, axons in previous layer, we're doing first axon in previous layer. At the end here we're saying, okay, for the next layer, first axon in previous layer is equal to first axon in previous layer, which as we know is 0, plus axons in previous layer. So when we get to the layer index of 2, we should be seeing a different value here. I'm going to go ahead and debug our way through this. So at the point that we hit here, we've already done index of 0, and the first axon in the previous layer is 0. So we can step into this and, whoops, I accidentally hit F9. Okay, so we can step into this and we're going through, this should be layer index 1. It is. So the axons in the previous layer, well, there are 4 in the input layer, so that's correct. And the first axon should be axon 0. So we're going to go through this for loop, and I'm going to go ahead and breakpoint here. So at this point, the first axon in the previous layer is 0, but we're going to add 4 to that. So the first axon in the previous layer is now axon number 4. And is that correct? Axon number 4. Yes, that's correct. The first axon in the previous layer is 4, and we're going to increment the layer index. So we're now at axons in previous layer. Well, actually now that value should be 3. So we've got the hidden layer axons. The first axon in the previous layer is axon 4. So we're going to start with that, and we're going to say the axon index for the first one should be 4. So that's the first synapse that we're doing. We're incrementing that, and we're saying if it's greater than 4 plus 3, which it's not, we're going to loop around, and the first axon in the previous layer, AIDX is now 5, that's correct. AIDX should now be 6, that's correct. And then we are doing another loop where AIDX is back to 4. Why are we doing a 4th iteration through that loop? Because our layers are incorrect. Okay, so if we correct our layers now up here, then this should all work out fine. So our first layer, first axon is, or synapse is number 4, and we're going up to synapse 16. So let's see if that's right. We've got 1, 2, 3, 4 axons. This is our input layer, so we're correctly starting at 4. And then we're going to go 1, 2, 3, 4 for the first hidden layer, neuron, 1, 2, 3, 4 for the second hidden neuron, 1, 2, 3, 4, 1, 2, 3, 4 for the third hidden neuron. So we actually go up to 15. So our last neuron here is 15, and then the first neuron in the next is going to be 16, and the last, well, it should only go up as far as 18. So somehow our last neuron in these, or our last synapse rather, in these layers is incorrect. Let's go and have a look at the layer initialization code. So we're saying the first synapse is 0, the last synapse is the pred of the neurons per layer in the previous layer. So for the input layer, we're getting first synapse of 0, that's correct, and pred of layer 0's neurons, which is correct. So we have that one right. And then we're looping through 1 to the remaining layer number, and we're saying the first synapse is the synapse after the last one in the previous layer, which is correct. And the last synapse is F layer's first synapse plus this multiplication of the previous layer neurons. Okay, so I think we should be doing first synapse plus the pred of that value. So let's go ahead and breakpoint here and run through and check it. So we are now in layer 1, we should be in layer 1. Yes, we are. And the first synapse in layer 1 is number 4. That's correct, it's after our input layer. And then the last layer, well, that's going to be 4 plus something. So the neurons per layer in the current layer is 3. So there's 3 neurons in the current layer. And in the previous layer, as we know, there should be 4. So if we do, there are 4. So 4 3s are 12, and 12 plus 4 is 16. But what we actually want is 15. So we're going to do pred on all of that, because we're indexing from 0. Okay, so let's go ahead and see if that all functions now. If we run this, and I'm going to take out my breakpoints as I go, and that has run. Actually, I needed to do a clean all and build all, because I'm working with a package, and we'll give that a run. Okay, let's take a look at our output. And we're now up to 15 and up to 18, that's correct. So we're going, the first 4 synapses are our input synapses, and they point at 8 through 11. Let's just take those out since we no longer need them. Okay, so the next 3, we have 3 hidden layer neurons, and each one has 4 synapses. 1, 2, 3, 4. So that's the first hidden neuron. 1, 2, 3, 4. That is our second hidden neuron. 1, 2, 3, 4. That's our third hidden neuron. And these all point at axons 0, 1, 2, 3. So that's our 0, 1, 2, 3 neurons there. They're all taken out, so they're fine. And then we have 16 through 18 pointing at neurons 4, 5, and 6. 4, 5, and 6. So actually we have a 7th axon there, which appears to be completely irrelevant. So let's completely bring this all back as it was and see what's going on here. So the 7th axon, the 7th axon is actually the output of our output neuron. So that's all good and correct. So 7 is our output, and that's how we'll get our output from the network. So our network is configured and initializing correctly. In the next video, we're going to add the ability to, I don't want to save this. In fact, I'm going to go ahead and remove this project now. I don't need to dump my net. And I'm going to, before I finish up, remove the dump arrays code here. I don't need that anymore. The network is doing what it should on initialization. So I just want to strip that out with you so that you're aware that I've done that. And the other thing is, in the initialized synapses, the initialized axons, we put this 200 value in, which we no longer want. We're going to initialize everything at 0. Okay, so that's all saved off, and in the next video we'll look at putting some input into this network and then see if we can't process it for an output. So until next time, thanks for watching. My name's Craig Chapman.